Great. So today we're looking at an interesting CTF, still working through the Quill CTFs, and we're working on the PandaToken CTF, which I dropped in our core chat. But here it is again, if anyone wants to take a look. And I will share the code and we'll start diving through it. So our goal in this CTF is to have 3 tokens in our account. And so what we have here is they provide us with this Panda token, which is a ERC20 that they've modified, and we'll go through that. They also provided us with some default Foundry code for us to test this in Foundry. And Foundry is what I usually use to test anyways. It's kind of what they want us to use here too. So we have a little bit of insight from how this test is set up, implementing the attack here. But let's take a look at specifically what's happening here, kind of get a sense of the code. So we know it's an ERC20. We should all, I think everybody here is mostly familiar with that. They have a public variable that they're storing. They have 2 mappings tracking to one to signatures and then another one to burn pending. So we'll see kind of how that gets used throughout the code. Mint, this looks pretty standard at first. The constructor, okay, so we see that they're giving us likely the C1 variable here in the constructor. Then they're also passing in token name, token symbol, and then they have this block of assembly. And so we might dive into this. Let's see what the rest of the code kind of demands of us, and then we'll dive into this if we need to. Sometimes the CTFs have some kind of like head fakes, so don't want to spend a bunch of time someplace that we might not need to. So we'll keep going. Calculate amount is obviously like obfuscated with their variable naming. There's a couple ways to get around this. Like oftentimes I'll just throw something like this into GPT and ask it to provide clean variables. Another easy way is to ask yourself like what's actually being used. So okay, this is what's getting returned. So I see that's what's getting returned is partially defined at the top. It's being set equal to this division, and then what's actually being used within here. So like that's the input. A lot of these variables here aren't even being used. So if we need to dive into this, we will. Calculate amount probably will need to. All right, let's see. Get tokens. So this is probably a spot for us to be looking. You're inputting an amount and a signature. So it asks us, so we do need to know calculate amount. So we'll have to take a look here. I'm just going to add a look here. So we'll go back to that. Then here, let's see what we're doing. We're hashing together an encoded message.sender and gift amount. Gift amount is based off calculate amount. And then we're setting RS and V, which are the elliptic curve variables defining the signature. So then what we're doing here, assembly, let's see, loading in some information from the signature. And then here, address gift from, it's recovering the signer address from the signature variables and the message hash. So this is like a built-in function. You'll see this used in like places like forwarder contracts for gas lists, like meta transactions, things like that, where instead of actually executing the transaction directly, what you're doing is signing a transaction, which is then validated on chain in a smart contract to ensure that the person who is supposedly had signed that transaction did actually sign that transaction, and that none of the objects within that signature have changed. So what it looks like here is basically what's happening is burn pending. So after they check the signature and who the gift is from, so they're saying burn amounts from this individual. So what it seems is happening is that to transfer funds, you sign a transaction that defines the amount and who the tokens are being sent to. And then once that's been confirmed, they're saying, okay, we're going to burn the amount that's sent. We have a valid signature here, so we're going to burn the amount that was sent to them from the person who is sending it. And then this is an interesting line, require amount equals 1 ether. So this is a ERC20 contract, so we're not actually moving around ether, right? What we're moving around is, Panda tokens, however they define that. And so really what this is doing is this is just 1 ether is just casting the number to be 1 times 10 to the 18, right? Is equals 1 ether. So essentially what this is saying is amount should be equal to 1 times 10 to the 18 Panda tokens. And ERC20s usually are defined to have 18 decimal places. So, 1 ether, you can kind of just mentally swap that out with the ERC20 as well. We're just casting the number. So we know that when we call get tokens, we need to be requesting an amount that's exactly equal to 1 ether. So we know that the challenge is telling us we need to extract 3 from the contract. So we're going to need to call this function more than once. This line here requires that the balance of the individual sending gift from, that's the individual who is sending the funds, minus burn pending of that sender. So it's basically saying ensure that the balance minus the amount that they've committed to send is greater than or equal to the amount that is trying to be sent or received by calling get tokens. If not, then we get a error of balance. It's not the most helpful error message, but if you see balance when we're going through this, it's because this required statement is throwing. The next required statement, so use signatures. So this is checking to make sure that the signature being used to claim these funds isn't used more than once. It's like a replay protection, it seems, so that you couldn't just continually recall using the same signature. So after using the signature once, the signature can't be used again. So each time we call get tokens, we will need to pass a new signature. Thank you, Copilot. And then it transfers funds to the caller, the message.sender, by minting them tokens. And then at some point in here, I don't immediately see it. I would imagine the burn pending can be called and it will settle those funds. And it looks like here the owner could call the burn pendings, and for a specific user, burn any of their pending funds, it would appear. But that probably isn't immediately applicable to us because really what we care about is just being able to extract funds. So as of right now, going through this, we know that we need to be able to form a signature that will be able to extract funds from a account that has funds pending to be sent. Now, the assumption here, if we look at how this was set up, this is, again, the Foundry code. So in the setup, they're deploying the PandaToken. Note that they're passing in 400 for this C1 variable. So just keep that in the back of your head. And also, like, let's say that this is a real world scenario where we don't have, like, we aren't seeing the setup in Foundry. You can always get the constructor variables from the chain. So this is like still feasible. You would just go to Etherscan or something like that and grab the variables that were passed into the constructor at the time of deployment of the contract you're trying to attack. So PandaToken, it's defining it PND, okay, and then test. They're making the caller the hacker. They are creating a hash by encoding the hacker in 1 ETH. So basically saying, the hacker should be receiving 1 ETH. We're going to encode that, sign it. That's our message hash. And then it uses the Foundry VM.sign to generate the V, R, and S values. So remember, this is all defined by the CTF. I haven't written any of this code. Then you implement the attack, and then at the end of it, you need to assert that the balance of Panda tokens for the hacker is equal to 3 Ether, aka 3 PND. It's just, again, casting that number. So given this setup, we know nobody else has transferred funds into the contract, right, via this setup. So given the get token, it's not like there's funds that a different account has transferred in that we can try and manipulate that account or anything specifically like that. So there must be funds, Panda tokens in this contract elsewhere that we can extract. And so outside of the setup here, right, we know that, of course, the other place that the contract is set up is in our constructor. So it seems like we do need to dive into the assembly here a little bit. So we can just take it line by line. So this first line, this position, when you're loading in hex 40, this is the free memory pointer. Did I hear somebody hop on the mic? No? All good? Okay, cool. So yeah, this is a special spot for the EVM. So what we're grabbing here is get the free memory pointer and load it into pointer. We got a little bit of help with this variable here, in case you weren't familiar with that. Then the second line is saying, well, Copilot is close, but store the value in slot, let's say storage slot 110. Multiply 1 times 110, so 110. So you're basically just saying S-load the value at storage slot 110 into the pointer to, well, not into the pointer, but like the location the pointer is pointing to. To note, again, the value of storage slot 110 at this point in time is likely 0. That's the hypothesis. I haven't seen anything that would give me a reason to believe that it's not 0 there. Okay, Copilot's trying to beat me to the explanation. So this next line here, you're going to store the, so add pointer. So this is one word, right? 32 bytes. So what it's saying is you're adding 32 bytes to the free memory pointer, and at that location in memory, store the value 0. So add 32 bytes to pointer and store the value 0 at that point in memory. All right, we're making our way through it. So now we're going to be defining a slot by taking the hash of the 64 bytes starting from the point of the pointer. And so remember, this didn't this line here isn't progressing the pointer. It's just using the pointer as a reference, adding 32 bytes and storing this. So the pointer, we know that we have the first word is the value of the storage slot at 110, so is likely 0. Second word we know is 0, right? And then it's hashing those two together. So this is starting to feel familiar to a primitive that we have in Solidity. So start thinking about storage primitives and what that might be. But we just took two values from memory, took the hash of them, and defined that into a slot. Now what we're saying is store at that slot, so the slot that we defined here. So at slot, storage slot, store, and what's happening here? So we have 3 times 5, 15, plus 4, 19. So, and this is exponential, so 10 to the 19. Store 10 to the 19. All right, what just happened? We know, again, so like 10 to the 19, this should maybe start throwing some alarm bells. We know that ERC20 decimal places are 10 to the 18, right? So this to me looks like a token value saying this would be equivalent to 10 Ether or 10 PND tokens. So at this slot, we're storing, the slot defined by this, we're storing a value that could be equivalent to 10 PND tokens, right? So what is this slot, right? So we just put together 0 and 0, took the hash of that to define the storage slot. So this feels a lot like a mapping, and that would make sense given the token types. So for anybody who isn't familiar with like the layout of storage variables in Solidity, I'll direct you to this. So the mappings and dynamic arrays in Solidity have some like special definitions for their data and where it's stored in storage. So if we find mapping, there we go. So mapping here, the corresponding value of a mapping key K is located at the KEKAC 256 of h of k dot p, where a dot is the concatenation. And h is a function applied to the key depending on its type. And for value types, it's just padding that to 32 bytes. So what we did here was we had h of k was presumed to be 0. P was also presumed to be 0. So we're at the location of P, they define P up here. So assuming the storage location of the mapping or array ends up being a slot P after applying this, like the standard storage layout rules. So P, it's saying that whatever is in slot 0 based off of the standard definition of Solidity's storage packing, that's the mapping we're looking at. And then taking the key and padding it. So it's taking a key of 0 for a mapping stored at the 0 slot naturally, and placing 10 to the 19 in that slot. So given this, we know we're in an ERC20, right? So I'm switching back. I'll remember to switch you back to my code. So what's the first mapping in the ERC20? It's balances. So what it seems is happening in the constructor, one of the things that's happening in the constructor is funding essentially the zero address, because remember, the first zero is the key, the second zero is the slot. So we know slot 0 is this mapping, the key is an address, so the key is 0. So the 0 address is being funded with 10 PND at the outset. So all of a sudden, we know that there is 10 PND that can be extracted from this contract. I'm going to pause there quickly. We just ran through a lot. Are there any questions on that? No? Cool. Well, as we go, as always, feel free to like drop questions or comments in the chat, and I'll keep an eye on that. So we can keep going, but I think, let's see, from memory, load into the pointer, whatever exists at storage slot 5. Here, we can see that in storage slot 6, add the C1 value, which recall from the Foundry setup, we know is 400. So while we're here, we'll just say that. So value of 400, whoop, stored in storage slot 6. Okay, then the rest of this we may need to come back to, but I want to explore the fact that we know that at the 0 address, there's 10 PND. So back down here, we know that if we could get the gift from, we know has a balance of 10. Burn pending should be 0 until we call this. And then amount we know is going to be 1 ether. So we know this require statement we can pass because we can call this more than 3 times before we run into an issue here. So we know that this will pass even if we are only calling with 1 ether each time. Burn pending gift from, even if this increments, that's okay. So then really the question is, gift from, we need to be able to pass a value into ecrecover that will spit out the 0 address as the signer of this message hash. So also, like, always good to look at imports, see if there's anything that's being like casted, right? So we see Open Zeppelin, these are standards. So we know that what's being used here is just the standard ecrecover function that's in Solidity. So let's see, can usage of record make more easy to read what the contract is doing on the constructor? Oh, this is, that's really interesting. Let's try this when we do the walkthrough. This is in Foundry we would do this, right? VM.record new Panda. Yeah, okay, yeah, let's definitely do this when we get into the test. Or I guess we could just do this right now real quick. Just comment this. We'll say function constructor view, public or external, either one. I'm just gonna copy your code, Anon. New Panda, we can just copy their input. Or I guess actually we don't even need this because we already have it from the setup, right? Or no, we need it because we're looking at the constructor. I see. Address nums contract. Nums contract, what are we doing here? Is this...
So I think that you should put the Panda address token there.
Okay.
Yeah.
So we'll say Panda.
So the main idea here is that you will have in an array of all the slot numbers that you are reading or writing, and then you could, well, you will have those numbers only. But after that, you could see what's inside of each of these slot using the vm.load. So you could make a loop.
Okay.
To just console log all the writes and what's inside on that slot.
Got it. Okay.
So this might be helpful if you already have some intuition of what's doing in the constructor and you want to confirm it. You could use this.
Cool. Yeah, that's good to know. I think what we'll do, I'm curious because I haven't used this vm.record before. So we'll keep running through the attack based off of our current assumption.
We could trade later.
Yeah, and we'll try this at the end because I'm definitely curious about that. Okay, so who knows like the core issue with ecrecover? I think Anon probably knows, given he's written a bunch of these CTFs. But does anybody else know the issue here, or the common vulnerability with ecrecover? Okay, so when I hover over it, it actually is giving us the answer. So recover the address associated with the public key from elliptic curve signature, or return 0 on error. Return 0 on error. So 0 on error, it does not throw an error. So all we need to do to exploit this is to pass in a bad signature. Pass in bad signature values, and it will return the 0 address. And then all of a sudden, gift from is the 0 address, which we know has been funded with 10 PND tokens. And so that is a critical aspect of the CTF here, and is likely kind of like the crux of how the CTF was written. They wanted to see if people knew about this issue with the ecrecover. The reason I was checking imports is OpenZeppelin has a safe ecrecover that will throw if it returns 0. So that's something to watch out for, is that if this returns an error, you get the 0 address. And so they just added a little bit of complex assembly to obfuscate the fact that they funded the 0 address with 10 tokens at the outset. Okay, so we know that if we pass in a bad signature, everything from here down, we can withdraw 1 PND token each time we call this. But the question is gift amount. So the last thing we have to look at, gift amount. What is, how is that being used, right? I actually don't even know if it matters that much, since we're gonna be passing in a bad value here. But for the sake of just the exercise of going through some ugly code, what's going on here? So we're gonna divide the multiplication of the input. So remember, amount, this has to be 1 ether. So what's passed into calculate amount is 1 ether. So we're going to multiply 1 ether by 1,000. So 1,000 ether. Just going to put this here. 1,000 ether divided by, this is divided by the addition of 599 plus 1 plus S load 6. Remember S load 6, 400. So 400 Okay, so this function is doing absolutely nothing. It's doing 1,000 input divided by 1,000, which equals input. So this function does nothing. It's just a head fake to distract you and take up some of your time. So we know gift amount is equal to amount. So we don't need to worry about that. So at this point in time, we should be comfortable with going ahead and writing our exploit. So I have this shell of a attack contract. I always like to, you could write the attack like, directly in here, and that makes it a little bit easier to like immediately understand and maybe test it. But I always like to write a separate contract that you would have to deploy to make it a little bit more real world. So what do we have to do here? There's a couple things you always have to do. So function, execute, address, you need the target address, right? So this is going to be the PND token contract. And then we know from get tokens, we need the signature. So we have from the setup these VRS values. So let's go ahead and grab those values in our input as well. So that's uint_v bytes 32R and bytes 32S. Where is bytes 32? I didn't see in that ECC, made me sad. All right, so now we're, first things first, the see you do in almost all of these attacks, PandaToken. We're gonna cast the target address to the ERC20 token type so that we have all of the functions that are on the PandaToken contract. So that's all we're doing. We're just casting this so that it has the same ABI as the contract we're trying to attack. So now we know, let me maybe do a little bit of side-by-side action here. Everybody can see that all right? Yeah?
Yeah.
Cool. So what we're doing is PandaToken. We want to be able to, we're going to call into the PandaToken.get tokens. And we know we need a loop, but I'm just going to do the normal logic first. PandaToken.get tokens. We know we need to send 1 ether exactly. And we need to pass in a signature. So we'll define that signature here. So bytes memory signature equals, normally the way we would do this is avi.encode rsv. This will give us the correct signature, right? But we want an incorrect signature. Really easy. Let's just say -1. Now this signature will not correctly calculate, and we will have the line here, ecrecover get from will be 0. So I'm just going to go back to full screen. So now we also know, okay, we need this to be a loop. So let's create a loop. So let's say for uint 8i equals 1. We're going to start with I equals 1, so we want to loop through this 3 times. So I less than 4. And then we'll increment I each time through. We'll grab this. Oops. One more. Okay, and then we'll just, because we know we need every signature to be different, when we loop through it, we'll just subtract v by different I, and it'll be a different signature. So this for loop here will extract 3 PND tokens, get 3 PND tokens into this attack contract. And then we want to transfer that. So if we look at this, we know that the assertion they're testing is that the hacker, not our attack contract, but the hacker has the 3 PND tokens. So we will go, and this is still, in addition to the novel transfer mechanism they've implemented, still in ERC20. So we're just going to transfer the 3 PND tokens to the message.sender. As always, I'll note that this isn't a safe contract to deploy on something like mainnet, right? Like somebody else could call it, you might want to set up a constructor, lock it down if you're actually to try and do a POC exploit. Or I often compare it to MEV bots, right? There's been a lot of scenarios where people have written MEV bots thinking simply about how they can extract value, but not keeping their MEV bots secure. So, we're just writing a little implementation, but doesn't mean that this is necessarily secure code. So something to keep in mind. Implementing the attack, it's pretty easy. Let's see, we have attack.sol already up here. We need to deploy a new attack contract. Copilot's helping me out here. And then we just say attack.execute PandaToken VRS. Does that all line up? It looks like it does, VRS. So now we can go ahead, jump into the terminal and give this a crack. Forge test. It's going to compile it for us. All right. This is taking longer than I would anticipate. Is my for loop somehow unbounded? Oh, nope, the compiler is just taking a long time. We got all these different Sol C versions, that's probably why. All right, and we passed. So that's the exploit. Core thing here is really just understanding, one, a little bit of the state variable layouts and storage. That's where the constructor was kind of getting at. It's do you understand how mappings are storing and accessing storage? A little bit of assembly in here, which is always fun. And then really, to me, this is the crux of it all. If you're ever using ecrecover, either you should be using a safe library or you should always be checking for a 0 output. Yeah, that's kind of the crux here. Let me pop open the chat. I haven't looked in a sec. Polygon lack of balance check bug fix. Oh boy, yikes. Cool. Any other questions?
So if I understand correctly, the problem here is ecrecover, generates a public address of a signature that may or may not be an actual address, is it?
So the issue here is that it returns 0 on an error. So you could have a public address, no problem, right? So we see this type of thing is used in production all the time with forwarder contracts where you're doing gasless transactions and you're checking within the forwarder to see whether the the signature is correct. And so the way that this works is you pass in a message hash along with the members of the signature, and it will recover the signer of this. And because of how the elliptic curve cryptography works, this is you would only be able to pass in the VRS values if you had the the actual keys for that address to sign that message. So it's one-way cryptography, right? Like you wouldn't be able to backdoor your way into uncovering the signer private keys or anything like that from ecrecover. So that isn't the issue, that is public. The issue is that when this has an error, if you pass in bad values, it'll give you the 0 address value. And this contract, this CTF specifically, they deployed 10 tokens at the 0 address, something that you would probably never see in production, right? But let's say that some contracts, let's say they decide that they want to burn their tokens to the 0 address, right? Or something like that. I mean, even that in this scenario doesn't exactly line up, but the 0 address is used for a lot of different things sometimes. And so you don't want somebody to all of a sudden be able to access the 0 address and whatever is attached to that in your contract by passing a malformed signature into ecrecover. Does that make sense?
Yeah, that makes sense. So you're saying that the contract does not handle incorrect signature, is that right?
Yeah, that's correct. So ideally what you would have here is something that's like, require this, right? Copilot's way ahead of me. If they had something like this hack would have been impossible, right? Or if they had used something like the Open Zeppelin library, which has their own like casted version of ecrecover, which also is doing an automatic check like this.
Yeah. On a side note, is this how transactions are signed on Ethereum using VRS and a message hash?
Yeah. So yeah, essentially you're taking, here, let me pull up. This might just be like a helpful illustration, is the Open Zeppelin, they have like a minimal forwarder contract. But essentially, yes. Or like I can drop some links. Either look at Open Zeppelin's minimal forwarder, or you can look at like Gnosis Safe is a great example, right? Because they're using signatures to validate transactions. So essentially what is happening is you're taking the private keys and you're signing a message hash with those private keys to generate the VRS values. And so by the ecrecover, because it has the message hash and it has VRS values, it can recover the signer. As Anna noted, there's some other issues with ecrecover. So like you can manipulate a signature so that like you might not necessarily always have, like you can't use the output of or like rather using ecrecover, you can have distinctly different inputs which end up outputting the same thing with the same signature. So as you know, you could find another similar signature which could result in issues. So like you wouldn't want to use the signature necessarily as a nonce, right? Because theoretically that signature could be recreated with a slightly different input to the function based off of how the inputs are encoded, whether it's packed or not, things like that. So there's some common vulnerabilities around ecrecover and how signatures happen on chain that should be aware with.
Yeah, that makes sense. Thank you.
Cool. All right. I know we got a little bit of a late start today. I would love to take a look at this, but I think I might play with it offline because I got to get back to things since we got a little bit of a late start. But yeah, thanks guys for joining. I'll end up posting this sometime soon. And if you have any questions about the hack or the upcoming hack that we'll do, we'll just do the next CTF from Quill that's in line and we'll go from there.
All right. Thanks, Chief.
Thank you.
All right. Thanks, everybody. Have a great day.
Bye bye.